Solving ODEs with the power series is totally crazy and it's kind of fun. It's amazing. You can't help but get excited about it. Basically, the idea is we've shown that we can already solve problems like this. And they're like, yay, I can solve this because I can find a characteristic equation and do stuff and it's fine, but then if I do this or this, then it makes me sad. So basically, how do we solve problems that would otherwise make us sad? And the answer is with a power series. So this is this like formula thingy that basically says, if I have some polynomial in terms of x and some other polynomial in terms of x and some other polynomial in terms of x, then I can actually use a series, power series to solve it. And there's a couple of things. First of all, these polynomials should have no common factors, so you should obviously factor out anything because it'll make it easier. Also, if you have an initial condition, like say you had an initial condition that said y at some x naught was equal to blah. Okay, so there are some rules like p naught at x naught cannot be 0, because if it was 0, then you would end up dividing things and you get this singularity. It's called a singularity. So these are things that you want to watch out for. Generally, whenever you're solving problems out of a book, they're not going to give you ones that are unsolvable. But as long as you don't have a singularity, then otherwise, then it's an ordinary point like that. So, and we're happy. So singularities make us sad, ordinary points make us happy because we can just solve it. So the reason that we like having an ordinary point is that we could go through and we could divide out by p naught and not do any kind of divided by 0. But anyway, the basic idea is that if I have some kind of polynomial thingy with second order linear ODEs, that I can create a solution in the form y is equal to n going from 0 to infinity, an. And I'm going to give you two different versions. One is x to the n, and that's for initial conditions at 0. So like if I knew that y prime of 0 was blah, and y at 0 was blah and y prime at 0 was blah. Okay, but if our initial conditions are not at 0, it's still not a big deal. Then we would just make a guess of n equals 0 to infinity, an, x minus x naught. So if we had like initial conditions at x naught, then it would look like y at x naught is blah, 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 and y prime at x naught is blah, 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 blah. So really, it's just if you have a non-zero initial condition, then you want to guess x naught. If you have a 0 initial condition, you want to just guess x by itself. But aside from that, you just take derivatives, plug it in, and so the whole goal, then once you, basically you're going to guess this, or this, and then you just want to find your constants, a1, etc. So you just want to find the constants or a formula for those constants, which is usually what ends up happening. So that's nice. Okay. So let's give you an example to kind of play around with and see where we're going with this. So say that we had a Diffie-Q problem that looked like this. 1 plus 2x squared y double prime plus 10x times y prime plus 8y is equal to 0. And it also tells us that y at 0 is equal to 2 and y prime at 0 is equal to negative 3. And this problem says maybe compute the first 8, so say a0, a1, blah, 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 up through a7 as the coefficients for the solution of the power series. So essentially what it means is I've got this thing that's in the form, well, like I said, the polynomial with the little linear ODE in front of it, second order ODE. And my initial conditions are at 0. Whenever I plug in 0 here, I get 1. So that's non-zero, so I'm good to go. So I can totally guess my power series solution. So I'm going to guess, and by guess I mean I know ahead of time, that I'm going to get y is equal to n equals 0 to infinity, a sub n, and then x to the n. And I don't guess x minus x naught because my initial condition is at 0, so I can just guess x at 0. Now actually I can already compute the first two terms of this solution. And you'd be like, really? And I'm like, yeah, totally, check it out. So this is actually going to be equal to a naught times x to the 0, which is 1, plus a1x to the first plus a2x squared, etc., etc., etc. So I can actually already apply the first initial condition. So y at 0 is equal to 2. So y at 0 is equal to 2, so that's a naught plus a1 times x is 0 plus a2 times x is 0, 0, 0, 0. So I've actually already found out that a naught equals 2. Partial credit for the win. Yay! Okay. Now similarly, I can find, if I know what y is, I know what y prime is. It would be a1 plus 2a2x plus more stuff that's going to have x's in it, which is fine because if I apply my initial condition of y prime not being equal to negative 3, then that's a1 plus 0 plus 0. So that means that a1 is equal to negative 3. Not that I can do anything with this at the moment, but you know, it's always nice to feel like you've got something to start with. So I got the first two with no problem. The rest of them can't be that much worse, right? Ha 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 ha. Okay. We need a fresh sheet of paper to do this. All right, so remember, we have this guess, and I'm guessing n equals 0 to infinity, a sub n x to the n. Now, eventually I'm going to need to plug into my original equation, so I need to go ahead and find y primes and y double primes. So y prime is going to be equal to n equals 1 to infinity, and I'm going to pull the n out front, n, a n, x to the n minus 1. And there's a video reminding you how to do this if you're kind of like, what's going on? All right, and then I can adjust the indices if I want. I can add one, add one, and subtract 1. And I can also get that y prime is equal to n equals 0 to infinity, n plus 1, a, n plus 1, and x to the n. All right, so now I'm going to erase these like that, okay? Just so it's clean. All right, I just have two different ways that I have that written. Now for y double prime, I'm actually going to double prime this guy so that my indices are that much easier. So I'm going to y double prime that guy. I don't have to, but I'm just going to. N equals 1 to infinity. The n comes out front. N plus 1, a n plus 1, x to the n minus 1. And again, I can adjust those indices. Oh, I lost my 1. I can adjust my indices by plus 1, plus 1, plus 1, plus 1, minus 1. And I've got that y double prime is equal to n equals 0 to infinity, n plus 1, n plus 2, a n plus 2, x to the n. And again, I'm going to go in and erase these just so that everything looks nice and clean. You're like, why did I do all this? This is stupid. It's not stupid, it's fun, I swear. All right, so this is my original problem. Just in case you've forgotten, this thing plus 10x y prime plus 8y equals 0. So basically what we're going to do is we are going to plug in everything for all of these different stupid things and get answers. And I have nothing better to say than that. We're just going to do a ton of junk. Okay. For me, it's always easiest to go ahead and multiply everything out and kind of prep everything in advance, and I'll show you what I mean. And this isn't like an official strategy. This is just what I do because I feel like there's too much going on, and I get lost and confused inside everything. So I'm going to feel like I'm going to be running out of space, but we don't have a lot of options here. So I'm going to zoom out for a sec. So basically what I'm going to do is I'm going to prep all 4 of these. So I'm going to prep y double prime. Actually, y double prime is already in really nice shape. She's got a nice little series there, and she's already indexed at x to the n, so actually she's already ready to go. All right, then I'm going to prep this guy, and she's not ready because there's a 2x squared in front. So I'm going to make a note here in a second. I'm going to find 2x y double prime. Okay, now 10xy prime I'm also going to have to prep. So I'll make a note that I need to prepare a 10xy prime. And then 8y is actually in pretty good shape because I can just take this and put an 8 in front of it. There. Now I have an 8y. So that didn't take any effort at all. So whenever I need to plug in an 8, notice I'm putting the 8 inside the summation symbol, not outside, because I'm afraid if I put it outside, I'm going to forget it later. So there's an actual reason for doing this. Let's go back to what we have here. Okay. So essentially what I'm going to do is I need to find good solutions for 2x squared y double prime and 10x y prime. So I'll make her a little bit bigger so I have a little bit more space. I can write easier. All right. So 2x y double prime, sorry, 2x squared, and then y double prime was equal to, I don't really need that, y double prime was equal to, and I'm looking at the one just right here, okay? So is n equals 1 to infinity, n times n plus 1, a sub n plus 1, x to the n plus n minus 1, okay? So now I don't need that. So this is the blue one that I'm looking at. Okay? Well, actually, yeah, there we go. Okay. So what I need to do next is I need to go ahead and throw the 2x squared inside. So whenever I do that, I have 2 n plus 1, a sub n plus 1, and then x squared times x n minus 1 is going to give me x n plus 1. Alrighty? Then the next thing I want to do is I need this to be x to the n. So I have to subtract 1, subtract 1, subtract 1, subtract 1, and add 1. And that finally leaves me with n equals 2 to infinity, 2 n minus 1 times n, a sub n, x to the n. And then this is my final version that I'm going to go to press with on this one. Okay, so now see if you can look at your notes and do something similar for the 10xy at 10xy prime. So seriously, take a minute, see if you can do this on your own, because this is really important. So we have 10x y prime. I'm going to see which one of these I'm going to use. So I need a y prime. I'm going to use this one. And one of the reasons I'm going to use this one is because instead of this one over here, is because if I use this one and I multiply by x, then this term is going to become x to the n, which is precisely what I want. So I'm going to pull that down. So n equals 1, an. So n equals 1, en, and it's n x minus xn minus 1. So whenever I multiply this through, I've got n equals 1 to infinity, 10, an, n, and then the x becomes x to the n. All right, so now I've kind of got something marginally reasonable, and by marginally reasonable, I mean not reasonable at all. So that's my green part. So I've got a pink part, a yellow part, a blue part, a green part. And all those parts are going to get added together. And of course, you know, this is a giant, giant problem, so it's really hard to see what's going on. But here it all is kind of on one screen, just so you can see it for a second. And I'm going to go ahead and write it, and then we'll take care of it from there. So essentially what we end up with this guy is this guy here. Everything added together, it's color-coded from what we had before. And notice, very, very importantly, that since I plugged this into the equation, all of this actually equals 0. That's pretty much the most fundamental part. Then if you forget this, you may or may not embarrass yourself in front of a whole bunch of people while you're trying to explain this. Okay. So that's too big. There we go. So now what I'm going to do is, since these are, let's see, this one starts at 0, this one starts at 2, and at 1, and at 0, which means I can't quite combine them all yet. I'm going to make everything go ahead and start at n equals 2. That way I don't have to worry about things not matching up. Okay, so I'm going to apply this guy. I got to write out the terms for n equals, that's not an n. Here I've got to write out the terms for n equals 0 and 1. This is already at 2. Here I need to write out the term for n equals 1. And here I need to write out the terms for n equals 0 and n equals 1. Okay, so here I've got at n equals 0, I've got 1 times 2 times a sub 2 times x to the 0. And I'll go ahead and get through that. And here we go here. Now what you'll see is I've actually aligned these up, so everything in the first column is going to be kind of like constant terms, everything in the second column is going to be x terms, ooh, this is supposed to be yellow, and everything on the right column that's a summation is an x to the n term. And also it's really important to notice that this is all equal to 0, so I haven't dropped that equal to 0 yet, because it would be terribly embarrassing to go through this whole thing and then forget that. It'd also be terribly awful and also a complete waste of time to go through this and then do this math wrong. So I in no way just had to recover from that. So if you find yourself just making dumb mistakes, don't worry, everybody does it. That doesn't mean that it's it's okay, but it's not okay because you eventually have to fix it. But it's just part of the learning process when you're not 100% paying attention. So now what I'm going to do is I'm going to go ahead and I'm going to combine these by their coefficients. I'm going to put all this x to the zeros, all the constants together, all the x's together, and then all the summations together. Okay, and so then that's what that looks like. Now, as you're staring at this, you probably can see that, oh, there's a lot of places I could combine stuff. And sure, you can combine a lot of stuff. I just chose not to combine stuff yet because I want to make sure you saw what was going on. So you see that throughout this, we have not lost any terms, so it's always good to check. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Okay, so at least I haven't lost any major terms. I may or may not have copied something wrong, but I can be reasonably sure that I've got at least something going. Okay, and so now I'm going to go ahead and simplify. So after simplifying, I've got something that looks like this. Okay, now, believe it or not, you're super duper close, although it may not feel like it. So remember that this all equals 0 because I keep emphasizing this, so it really means it's 0 plus 0x plus 0x squared plus 0x cubed. So basically every single term has a coefficient of 0. This is extremely helpful because that means that I can go through and I can say, well, this is 0, this coefficient here is 0, and every single one of these coefficients here is also 0. And in this way I can actually calculate the A naughts and the A2 and 3 and all those kind of terms. So I know that 2A2 plus 8A naught is equal to 0. You're like, well, how does that help me? And you say, well, remember a really, really, really long time ago, like really forever ago, we had this right here, which is where we found, based on our initial conditions, A naught and A1. So I know A naught is actually equal to 2. So I can go ahead and I can plug that in. A naught is equal to 2. Sorry, I did that backwards. A naught is equal to 2. These are the kind of mistakes you really don't want to make. All right, so I've got, well, just A2 is equal to -8. I can do that relatively confidently. So A2 is equal to -8. Okay, I had also figured out earlier, so I have 6A3. This is my second coefficient. That's equal to 0. I'm going to go ahead and simplify that a little bit. A3 plus 3A1 is equal to 0. And I knew from earlier that A1 is equal to -3, so that tells me that A3 is equal to 9. Good? Okay, so those are 2 more. And I was just trying to find the first 8 or so 0 through 7. Now, that's all well and good, and that's actually not too bad. Where things can get a little bit more fun. So the problem is no matter what, how many times you do this, you always potentially get things wrong. So actually you go really far away. Okay. So now what I'm going to do is I'm going to look at the this thing right here, this coefficient thingy right here. Okay, so I know that that coefficient also has to be 0. So I know that this plus, I'm going to go ahead and factor this, so I've got 2n plus, I'll just do n squared plus 4n plus 4an. I know that that has to equal 0. And so I know that an plus 2 is going to equal to -2, and I can actually factor that a little bit more. N plus 2 quantity squared, a sub n. And then on the bottom, n plus 1, n plus 2. So that goes away, and that goes away. So I've actually got a nice little recurring formula that says n plus 2 is equal to -2, n plus 2 an, and n plus 1. Now this is good starting at n equals 2. I know that that's good because that's where the summation starts. So since I have a couple of other values now, so remember I had that a naught equals 2, a1 equals -3, a2 equals -8, and a3 equals +9, now I can go ahead and find the rest of them. So for example, if I wanted to find, if I let n equals 2, then that would give me a2 plus 2 is 4. So where I see an n, I'm going to put in a 2. So 2, 4, a sub 2, 2 plus 1. So I've got -8 over 3 times a2, which is -8, and that comes from right here. So all those go together. Okay, so that gives me some horrible number, 64 over 3. So they've stopped being pretty. Does that mean I should quit? Probably not. So n equals 3. I'll plug this in again. So that gives me a sub 5. N equals 3, that's 5. A sub 3. 3 plus 1 is 4. So negative 10 fourths times a3, which was 9. So 5. So I've got negative 45 over 2. And if I keep doing this over and over again, I get that a6 is equal to negative 256 over 5, and that a7 is 105 over 2. And you're like, yay, I answered the problem. I have no idea what I did, but I answered the problem. Okay, well, this is where it's really, 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 really amazing. So essentially, the idea is you've actually done a whole lot more than you realize, okay? And this is kind of weird, and you may not believe me, but I swear you have. Okay, so remember a whole long time ago, we proposed that the solution was in the form n equals 0 to infinity a sub n x to the n. You're like, yeah, I guess so. I'd have to review the video to make sure, but sure, I'll believe you, whatever. All right. So that meant it was a naught plus a1x plus a2x squared plus a3x cubed, etc., etc., etc. Well, these coefficients here are the coefficients that we just calculated. So that means that our solution is desperately, really, 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 and truly, and you still can't see them all, so I want you to be able to see them all. Our solution, thank you, is really and truly that y is equal to a naught, which was 2, plus a1, which was negative 3, times x, and then a2 was negative 8, x squared, a3 was 9, x cubed, a4 was 64 thirds, x to the 4th, and then minus 45 over 2, x to the 5th, minus 256 over 5, x to the 6th, plus 105 over 2, x to the 7th, and more and more and more. So really, one of the reasons that we haven't been able to solve something like this before using traditional methods is there really is an infinite solution. This is an infinite series. These numbers just get bigger and bigger and bigger. Or not bigger and bigger, but the number of terms just goes on and on and on forever. Literally goes on forever. But here's what's absolutely super crazy, ridiculous, amazing, is if I go plug this into my original equation, I'll start to see that in fact the terms cancel out and it does go to 0. So to show you how this is, we're going to go ahead and do this at least once. So if I take the first derivative, the 2 goes away, and I'm going to take the derivative. Like that there, and then I'm going to go ahead and take the second derivative. And then it all goes along like that. Now, let's go back to what the original equation was. So that's what we originally had. Now the next thing I'm going to do, and it's going to look really goofy, actually let's go ahead and multiply this out because that's just going to make the math a lot easier rather than trying to do distributive multiplication across this. So I've got this, and I'm actually going to erase this just so we have a little bit more room, okay? So now what we're going to do is we're going to take those infinite series and we're going to plug them in and see if in fact we do get solutions that come out to 0. And you should already get a little bit excited because if you look here, you see a lot of those ugly fractions have started to go away, actually rather quickly. So I'm going to plug in for y double prime here, and then here. Then I'm going to plug in for y prime here, and then I'm going to plug in for y, just so you have an idea of what's going on. Okay, and this is going to look something like this, okay? So I'm not really expecting you to like write all this out. I'm myself using copy-paste for a lot of this, but at the same time, I think it's important for you to just kind of see it once so that you're convinced that it actually works, because sometimes doing an actual mathematical proof doesn't really convince you of anything except that you're confused. But whenever you see the numbers all kind of cancel out, then that's when it gets really exciting. So I'm going to go ahead and multiply it out, and you don't have to watch me, so hold on. Okay, and so that's what that looks like. Now, I stopped listing the terms, x to the 5th, because if I didn't have terms for all of them, it wouldn't help, and I didn't feel like finding more coefficients, because I really think you're going to be convinced at the end of this. So see, I arranged these all like this, and what is absolutely amazing is if I add these up, minus 16 plus 16 is 0. These 54, 30, and 24, 0. This here, 0. This here, 0. Even this, and I can prove it because I did it on my calculator. So I've got this 1536 right here, plus 2560 over 3, plus 512 over 3. That still turns out to be 0, and the next column is 0 as well. So basically you have, in fact, solved this differential equation by using an infinite number of coefficients on this power series. So this is very, very, very cool. And just really neat. Obviously, it's something that for a larger problem you would probably want to figure out a way how to program it, but it's one of those problems that we can actually solve by hand if we needed to, and hopefully now that you're convinced that you actually do have the full solution. So the full solution to this equation, this differential equation right here, is this. Or we could give it in terms of a sub n and give them this little formula. So really what you would do is in real life you'd give people the first two and then say, here's a formula, check out as many of those coefficients as you want, but I'm done. Drop the mic and head on out.